All right, so in this module we're going to talk about this video clip. We'll talk about forces. I will probably repeat some things that I've said in ModSim, but sometimes repetition isn't a bad thing. And we're basically going to ask the question, what do we actually mean by a force, and what are the different types of forces? So what is force, and what types exist? Well, if we start with the first question, what I mean by force is an interaction that causes a change in the momentum of a particle or of a system. And P here means momentum. So any sort of interaction between two particles or between two systems that causes the momentum of one, or actually that must cause the momentum of both systems to change, is what you would call a force. You're probably more familiar with the sort of idea that force is the thing that causes acceleration, but if you think about it, acceleration is sort of the same thing as change in momentum. So fundamentally, force is an interaction. That means you actually have to have two things involved because it has to be between two objects, right? So that's sort of what we nominally mean by what a force is. If we think about the second question, what types of forces exist, there really are a couple of categories that we can think about. So I'll start with the category of, so this is types of forces. You can break types of forces down into two broad categories. One category is the fundamental forces, or the fundamental interactions. And these are the types of things that sort of theoretical physicists spend their time trying to figure out and describe. They're the sort of basis of the theories that we use for describing the universe, and the sort of idea is that these fundamental interactions actually are the cause of basically all interactions that we see in daily life. And then the other type of force that you end up talking about a lot in the mechanics class is phenomenological interactions. And what I mean by phenomenological interactions are actually interactions that are due to fundamental interactions, but that have sufficient properties that are consistent that we actually build some kind of model that says, okay, in general, this system behaves in this way. So we build a phenomenological model for how the interaction behaves, even though in fact that interaction is much more complex than the model and involves a lot of fundamental interactions. Let me blow up fundamental interactions a little bit just to make clear what I'm talking about when I talk about fundamental interactions. So if you sort of ask the question, what does sort of physical theory say about the way that the universe works? One sort of framing of that is to say that there are four fundamental forces or fundamental interactions that explain everything about the way the universe interacts. And those fundamental forces are the strong force, the electromagnetic force, I'll write that as E and M for electricity and magnetism, but it's the electromagnetic force, the weak force or the weak interaction, and finally the gravitational force or the gravitational interaction. So the idea of sort of fundamental theory is that any sort of interaction that you're interested in, whether it's friction or drag or a spring or a normal force or whatever it is, or some nuclear force, all of those things are manifestations of some combination of these four fundamental interactions. So the idea is that these four explain everything. Now, it might not be convenient to use them to explain everything, but the idea is that you can use them to explain everything. We can compare these a little bit to think about how important each of them are from a day-to-day perspective. And in comparing them, there are two sort of categories we might compare them on. One category is strength, and the other category is length. So the idea would be sort of how big is this interaction? Is it a strong, is it an interaction that's really powerful, or an interaction that's kind of pathetic? And then how long a distance does this interaction act over? So to compare strength, we could start by saying, okay, let's say that the strong interaction has a strength of 1, just a sort of non-dimensional strength of 1, just so we can sort of compare things. If the strong interaction has a strength of 1, electromagnetic interaction is about 10 to the minus 2. So strong interaction is 100 times as strong as the electromagnetic interaction. The weak interaction is maybe, say, 10 to the minus 9, 10 to the minus 10. So it's a lot weaker than the strong interaction. And finally, the gravitational interaction is something on the order of 10 to the minus 40 times the strong interaction, which is kind of interesting if you think about it, because in fact, in daily life, it feels to us like this gravitational interaction is kind of the one that we know about. Like you can jump up in the air and you fall back down, and that's due to gravitation. Whereas we in daily life don't really feel like we see a whole lot of strong or weak or even an electromagnetic interaction. But strength isn't the whole story, and that relates to why it is that we actually experience gravitation more than the strong interaction. The other is length. And it turns out that both the strong interaction and the weak interaction are very short range interactions. And when I say short range, what I mean is that their strength drops off exponentially with distance. So nominally I could say that it goes as e to the minus r or as e to the minus r over r, depending on what you're talking about, but it drops off really fast, right? So the strong interaction and the weak interaction are short. And on the other hand, the electromagnetic interaction, the gravitational interaction, you've probably seen before that the gravitational interaction is a 1 over r squared interaction. The electromagnetic interaction is a 1 over r squared interaction, which are both long-range interactions compared with the strong interaction and the weak interaction. So these two interactions, strong and weak, really only apply inside the nucleus. You need to have particles really close together in order for the strong interaction and the weak interaction to matter, whereas the electromagnetic and the gravitational interaction can act over a much longer length scale. Obviously the Earth orbits around the Sun, and that's quite a bit longer length scale than the strong force or the weak force acts over. So that's actually the reason why we experience gravitation. The other comment I would make is that most of the other forces that we experience, whether it's the fact that you don't fall into the floor, there's a normal force that holds you up, or the fact that a spring works, or the fact that friction works, or the fact that airplanes are held up in the air by lift, all of those forces actually, when you sort of decompose them and ask what's really going on here, all of those other forces that you talk about are actually electromagnetic forces in the end. They have to do with the electromagnetic repulsion between atoms and the fact that atoms don't like to overlap with each other. That's an electromagnetic interaction. So really, a lot of our daily existence, most of our daily existence, is actually mostly explained by electromagnetic interaction. Quite a bit of the macro scale things that we feel are explained by the gravitational interaction. And then the actual existence of atoms and the behavior of atoms is explained in part by the electromagnetic interaction, but also by the strong and weak interaction.